This is January 2016, paper number 1, and this is question 8. This is a long question, so settle in. So we're putting this magnet into a coil of wire, and when the south goes in, this pointer goes to the left. Describe 2 ways that the student can make the pointer move to the right. So there's 3 different ways you can do it. You can reverse the magnet. So you can put north in instead of south. You could change the wires around. Change the wires around on the ammeter. So that would measure the current going in a different direction. And the third one would be to move the magnet out of the coil rather than into the coil. So south is going in. If south goes out, then it's going to go in the opposite direction. The student has a bicycle dynamo. These are the different parts of the dynamo. We're asked to identify what Y and Z is. Z is going to be a coil of wire. Terrible handwriting. That should be an R. Coil of wire. What does that leave Y to be? It's right next to the coil of wire, and it should be spinning. So that's going to be our magnet. Okay. Then these are the maximum output voltages from that dynamo. So you can see as it spins, it's going to have 2 maximum outputs per spin. So here's it going round once, and it going around a second time, and there's 2 peaks for every oscillation. So state the maximum. Just state, so it's just 1 mark, the maximum output voltage of the dynamo. Well, if you measure it off here, it's actually 1.6 volts. Calculate the frequency of the output voltage. Okay, so it has a time for oscillation of 0.4 seconds. Because look, if you made it hard for yourself, you could go from the top of this peak to the next peak, and that would also be 0.04 seconds. Easiest thing to do would go from this point to this point, where it hits 0.4, and then look, to do that next wave is another 0.04 seconds. So in the very beginning of this paper, it gives you this equation. And that's why it's only 2 marks for this calculate, because it's a given equation. So all we're looking for is that, and that would equal 25 hertz. This T means time period, and that's the time period for 1 oscillation. So next, which row of the table is correct when friction wheel turns faster? So the output voltage, well, if it's turning faster, we're going to have a higher output voltage. So it's B or C. Now the frequency of output voltage, so if you can see this, those voltages, would the frequency go up? Yes, because it's turning faster. So these 2 voltages, the maximum voltage would happen faster. So the frequency would go up. So it's got to be C, higher and higher. Apart from changing the speed of the friction wheel, suggest how the output voltage of the dynamo could be increased. This is a very obvious one. You could use a stronger magnet, and then you get more field lines being cut because there are more field lines from the stronger magnet. Or you could have more turns on the coil. So if there's more turns, you cut more field lines because there are more coil to cut the field lines. The student cycles for 290 seconds. Her dynamo produces a constant useful output of 3.1 watts and is 72% efficient. Calculate the total useful energy output. So first of all, what's the equation for useful energy output? So energy equals, it's going to be work done. So work done equals power times time. So remember that a watt is joules per second. And if you're looking for an energy, you're looking for joules. So if I want joules to be by itself, this would be joules per second. I'd have to multiply it by seconds. And then those 2 would cancel out, and it would just leave me with joules. So what I could do, if I didn't know this equation, I could just use the units. So power is joules over seconds. What do I need to get rid of that seconds? Well, I need time measured in seconds. So multiply those 2 things together. So it's 290 seconds is the time, and 3.1 watts is the power. So the useful energy output would be 900 joules. State the relationship between efficiency, useful energy output, and total energy input. So this is going to be our efficiency equation. So efficiency, I'm just going to do this quickly, efficiency equals useful energy output divided by total energy input. Okay, so there's our equation for 1 mark. Then we're going to calculate the total energy input. So the total energy input, so if we rearrange this, so input equals useful divided by efficiency. Now, I think what people would do and get this wrong is they would leave that efficiency as a percentage. So they would divide it by 72. But that's not right because it's 0.72 efficient. So you can't leave this in percentage because this would be a number divided by a percent, and that's not right. So we would divide this by 100 to get it back to the number that it was. Because remember, if we work at this, 0.72, that's the efficiency. So I'm going to have to put that back into here and multiply it by the 100 in order to get myself a percentage. So I'm going to have to take it back to the number it was in order for it to be a good number to use. So this one, so useful energy, that's 900 divided by 0.72, and then that would give me 1200 joules. And that is question number 8.